Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the relation between gravitational potential and gravitational field intensity. So in this case, you can see that there is a mass m here, and it is creating some gravitational field at this point. And let us displace this mass in this direction or in this direction by a small amount dr. Okay, so in displacing this mass in this direction by a small amount dr, you can see that the gravitational force would be pulling this mass. So the work done dw by the gravitational force dw would be equal to F gravitational dot dr. Okay, so this is the work done in displacing this mass, and you know that gravitational force is conservative in nature, so we can say that the work done by any conservative force is always in order to decrease the potential energy, and we can say that the work done by this gravitational force would be decreasing the potential energy of the system. So this work done would be equal to minus of du, a decrease in potential energy, and therefore du will be equal to minus of F dot dr. And if we need to calculate delta u, then we can say that it would be equal to integration of F dot dr with the negative sign. So this is minus integration of F dot dr with the negative sign. Now we know that the gravitational force is equal to gmm by r square. So let us substitute this value and let us see that what is the result. So now if we say that this vector form of this force will be like that, this is r cube and this is r vector. Okay, so if we see that this is the potential energy and we need to find out the potential, so dv is equal to du by m, which we have already discussed, that potential is equal to potential energy per unit mass. So dv would be equal to minus of, in fact, plus of du by m, and du is equal to minus of F dot dr divided by m. So F by m is gravitational field intensity. So dv is equal to minus of integration I dot dr, where I is the gravitational field intensity. So this is the relation between this gravitational potential and the gravitational field intensity. And when we are writing du, then we can eliminate this integration sign because this is a small change. So this is the relation, and if we find out delta v, then delta v will be, this is delta v, and it would be equal to integration minus of I dot dr. Okay, so this is the relation between the gravitational potential and gravitational field intensity. This negative sign indicates that on moving in the direction of gravitational field, potential decreases. So this is the significance of this negative sign. Now let us analyze the gravitational potential due to a hollow sphere by this formula. So we know that inside a hollow sphere the gravitational field intensity is 0, and on the surface of the hollow sphere, like at this point, so gravitational field intensity is gm by r square. Obviously I'm talking only about the magnitude, and this r would be the radius of the sphere, so it would be capital R. And at some point away, the gravitational field intensity would be I is equal to gm by r square. So let us find out the gravitational potential at this point P, which is outside. So when first case is the case when r is greater than r. So let us see that we are taking this mass from P to infinity. So we are moving in the opposite direction of gravitational field intensity, because gravitational field intensity is pointing towards the sphere and we are moving in this direction. So let us suppose that this is dr. So we know that dv is equal to or delta v is equal to minus of integration I dot dr, and delta v is the voltage or the potential of the final point, which is infinity and the point P, and this is minus of integration I dot dr, where I is gm by r square and dr. Now you can see that I is pointing in this direction and dr is pointing in this direction, so there would be a negative sign, and this is cos 180. So this would be 0 minus Vp, and it would be plus cos 180 is minus 1 gm and integration of dr by r square. The limit would be from r to infinity, and therefore minus Vp is equal to gm of integration of 1 upon r square is equal to minus 1 upon r. So this is minus 1 upon r, limit is from r to infinity. So you can see that potential at P would be minus gm by small r. So this is the formula for the gravitational potential at a point outside the sphere due to a hollow sphere. Now at the surface, we can see that at surface r is equal to r, so gravitational potential at surface will be equal to minus gm by capital R. Now we know that I inside the sphere is 0, therefore dv inside the sphere will be 0, because dv is equal to minus I dot dr, which means v inside the sphere would be constant, and constant potential means that the potential at all the points inside the sphere would be equal to the potential that has last unchanged value, which was the potential at surface. So v inside would be equal to minus gm by r at all the points inside the sphere. So this is the potential inside the sphere and it is constant. So if we plot the graph of potential, so it would be negative, obviously minus gm by r, and it would be constant, and till r is equal to r it would be constant, and that it would be a hyperbola like that. Okay, so in the next video I'll be bringing some more concepts of the potential due to different objects like solid sphere, wire and ring. Thank you.